Hello and welcome to this video lecture. In this lecture, we're going to, or this next sequence of lectures, we're going to talk about the modeling of dynamic systems. This first lecture will be broken into two pieces, two parts. One will be the background discussion, and then we're going to have a series of examples that are associated with this first part, and I'll probably do that all on this one OneNote page, though again, the videos will be broken up separately. And then we'll get into a second lecture that will have examples as well, but we'll be introducing some of the dynamic modeling associated with particular elements that we could see in a dynamic system. So there we'll get a little bit more down into the details of, okay, when you see this, you have this, etc. Now, again, I'm going to be relying a bit on your background knowledge for dynamic system modeling. So, hopefully you remember what's going on with masses, springs, dampers, etc. So this particular first lecture in both parts will be relying on that background knowledge. So if you haven't been exposed to it in a little bit, you may want to spruce up your, break off the rust and spruce up your knowledge about that a little bit and go and review that. So with that, let's go ahead and dive into the background discussion. So as I said, we're talking about modeling of dynamic systems. And of course, the first and very valid question that you might ask is, why would we want to be able to model these systems? And again, when I say modeling, I'm really discussing the development of mathematical models that describe the behavior of the system. So we are clearly interested in eventually controlling this system. So in order to do that, what has to happen first? So here I like to use a little bit of a counter example, which is I'm picturing a system in my head right now. I want you to control it. Now, clearly, if that's all the information I give you, that task is impossible because you have no idea what you're dealing with. So the very first thing that you need to understand is, what kind of system are we dealing with? How does it react? How does it respond to things? And then once we understand how it responds, then we can actually start trying to figure out ways to control it. And so because systems don't react randomly, at least for the engineering systems that we're dealing with here, hopefully they don't react randomly. What does that allow us to do? That allows us to use how things worked in the past, use our understanding of how physical behaviors and physical systems worked in the past so that we can predict how a particular system we might be interested in will work in the future. And so how do we capture that predictability? We capture it through mathematical equations, mathematical models that are associated with those physical behaviors. And then we can grab those mathematical models and put them together to form a complete mathematical description of whatever system we're dealing with and all the physical influences and physical effects that we need to capture for that system. So once we're able to do that, then we know what the system is doing, how it's going to behave, how it's going to perform. And then we can say, okay, do we like the performance or do we not? If we don't like the performance, then we need to go ahead and start modifying things by probably adding some kind of control element to the system so that we can then get the system to start doing what we want to do. But if we can never get to that first stage of understanding the behaviors of the system, understanding how a system actually functions, we're sunk. There's no way we would be able to try to control anything because we have no idea what we're doing to begin with. So, in order to control a system, clearly we need to understand its properties, because for that system I was imagining in my head, but I wasn't telling you what it was, you would have no ability to control it because you have no idea what the properties are. I wasn't telling you what the properties are. So you need to understand its properties. And again, of course, we as engineers capture those properties using mathematical statements and mathematical models. So here's where I like to bring in that little example that I just gave you, because clearly it's impossible to control an unknown system. You have no idea what it is. There's no way you're going to be able to control it, because that's what we rely on as engineers, is to be able to say, oh, this system will do this. So if I do this other thing, I will then be able to get that system to do what I want it to do. And that's all contingent on understanding the properties of that system. And so that's the whole point of this mathematical modeling of dynamic systems. So let's capture, though, that especially in this world that we're currently dealing with, that is working with rapidly responding systems, what they were doing back 100 years ago, where they were firing up a plant and the plant would just run for hours, if not days on end. What's going on with our rapidly responding systems? They're constantly being excited by different inputs that are changing in time, and then the system is trying to respond to those various changing inputs. And so here I'll just acknowledge that, yeah, back in the day, understanding the steady state behavior, not that it is unimportant today, because it is still something that gives us considerable insight into what's going on with the system, but just understanding only the steady state behavior is no longer sufficient. But let me turn that O into an A. I don't know how it became an O to begin with. So understanding the steady state behavior of a system, unlike, again, 100 years ago, is just no longer adequate. So it isn't typically sufficient. We need systems that will respond quickly, which means that they're still in the transient, how the response is evolving over time, i.e. the transient response. So they're still in that transient phase, and then we may have another change to the input. So here I will say, but when we look at this first statement, the reason that's important is because understand that a lot of your undergraduate classes were doing just that. They were focusing on the steady state behavior of a particular system, which makes sense because, again, it gives us a lot of insight, but it's only a part of the overall picture of how a system will behave. So for us, of course, when we're looking at the controls or controlling a system, we clearly need to understand how a system will react as it progresses to steady state, if it ever gets there at all. So we'll have to understand how it gets to steady state as well as the steady state behavior itself. So some things that we are interested in is, of course, how long it will take to reach what we will call steady state. Let's do steady first before we get the state in there. And of course, as you might recall, this is related to the settling time of the system. We are also interested in some of the features that are associated with the deviation between what we wanted the system to do and what it actually did. One of the ways we can capture that is through something called the overshoot. So how much the system overshoots, and how long it will take the system to respond. So of course, that means that we've asked the system to do something different. We want that change to be instantaneous. Clearly, the system can't change instantaneously. And so then we're interested in that deviation from what was what we hoped the system would do and what it actually ended up doing. So how long it'll take the system to respond. And of course, that is associated with the rise time of the system. And so these are generally the main behaviors that we are interested in when we are discussing, let's say it that way, the transient response of the system. So when we are trying to figure out how the system is going to behave, of course, that is, and here I'll say it this way, this information is captured by the dynamic model of the system. And so why do we make this distinction between a dynamic model and a steady state model, other than what it tells us, which of course is very different? And the reason, one of the reasons that we make that distinction is not only because of that difference, but also the different mathematics that we use. The different mathematics that lends itself best to this kind of description or this kind of application. So if we are interested, of course, when we're talking about this dynamic model of how things are changing in time, so here I'll just say it this way: due to the way the system response varies, specifically in time for most of what we do. Well, what is the best mathematical tool, best mathematical concept that allows us to capture that? We're interested in how something's changing as time is changing. Well, doesn't that sound like d something dt? Absolutely. And so the best mathematical tool at our disposal, and a very powerful mathematical tool, is combining together derivatives of various order and or various orders and the potentially the function itself into combining those together into a differential equation. And so it turns out that differential equations are really the most efficient approach and a very powerful approach to describing, or most efficient approach associated with describing, the dynamic behavior of these systems. So you can start to see, though, why maybe folks usually started with steady state behavior in their classes, because one of the things is it usually took you a while to get to differential equations when you were studying math in your, back at the beginning of your higher education. So you really weren't ready to discuss this. And also it can get kind of confusing initially trying to throw in what's going on with the dynamic behavior of a system, in addition to just trying to understand the fundamental concepts of whatever class you're taking at that time: dynamics, fluid mechanics, heat transfer, etc. All of those, it can get kind of confusing throwing all of that in together. So it makes perfect sense that we segregate these things out so that you're exposed then to the understanding the basic physical behaviors themselves first, and then we can start layering this idea of dynamic modeling on top of it so that you can then see how those behaviors can change in time. So one of the other reasons, though, that folks may shy away from it a little bit is because, let's be honest, working with differential equations is a little bit more cumbersome. So let's go ahead and capture. A little bit more cumbersome than just working with math that or mathematical representations that aren't necessarily changing in time. So working directly, as we know, and here I'll just shorten this to diffie-qs. So working directly with differential equations generated. So these differential equations, of course, are going to be generated from the governing laws. So I want to bring in that point here. That's where those differential equations are typically coming from, is generally difficult and inefficient. So working with those differential equations is typically difficult and inefficient. So of course, what have people done? They've figured out ways to represent those differential equations that makes it a little bit easier on us. So we'll go ahead and look at a couple of those ways. One that you hopefully have already been exposed to, and one that may be a bit new to you. So here I'll just capture that as fortunately, people have discovered. And here I'll use the term discovered a little bit loosely because at least in the case of the Laplace transform, as initially formulated by Heaviside, it was just almost, no, this is what I'm going to do rather than discovered. So it was almost more imposed than discovered. And then people were left kind of trying to catch up, building the formal mathematical framework around it, but that's okay. So fortunately, people have discovered. We'll just go ahead and continue to use that word, two widely used approaches. And there are, of course, others, but for us as engineers, these are the two that we most widely encounter or most generally encounter, that allow, of course, the differential equations. Again, here I'll just say diffie-qs. To be represented in more manageable forms using Laplace transforms. That's the one that you hopefully have already been exposed to, and the one that we are going to be focusing on in this class, of course, which is state space methods. So just as a bit of a reminder, and because we are going to continue to do a compare and contrast between the S domain and the Laplace transform and what we are working with when we deal with these state space methods, let's go ahead and capture the highest level, or capture the Laplace transform at its highest level. So the Laplace transform is a transformation where we can transform some time domain function f of t into what we generally call, though it's a little bit of a misnomer, the frequency domain function capital F of s is equal to, and we'll just talk about the single-sided Laplace transform. So we go from t0 minus to t infinity of f of t e to the negative st dt. So we go ahead and evaluate that integral for f of t, and that will transform f of t, or map f of t, to this frequency domain function f of s. So here we'll say that maps, as you might remember, maps a. Now here, I'm going to be a little bit more of an engineer, because of course in your math class they probably mentioned the independent variable can be time, but they probably kept it more general. And here we're going to focus in on engineering. And for us, when we're looking at what's happening from an engineering perspective, though sometimes we might be interested in spatial, transforming a spatial function, we're really going to be more interested, much more interested in the transform of temporal functions, so functions of time. So I'm just going to go ahead and run with that particular predisposition that we have as engineers, that we're talking about time domain functions. So just want to make that note there, that of course that it isn't always going to be the case, but it is almost, well, it's going to be very frequently the case. And in this class, I'm going to essentially make it the case. So we're only going to talk about time domain functions. So time domain function 2, its corresponding frequency domain function. Now, technically, so I mentioned that there's a little bit of a misnomer here. Technically, it's really an S domain function. Generally, the frequency domain function is captured by the Fourier transform. But nonetheless, from a practical perspective, folks out in industry usually will call the S domain version of the function, they will almost always call that the frequency domain. So I'm just going to go ahead and start adopting that particular terminology here, since it essentially goes through all of industry, or is used throughout industry that way. Okay, so we go from a time domain function to a frequency, or we're mapping it, a time domain function to a frequency domain function. And as you might have seen, it is typically used in classical controls. To determine one of the main constructs that existed in classical, or that exists in classical controls, the transfer function. I'll just try to squeeze it in here. Of course, the transfer function, of course, is abbreviated as TF, quite appropriately. So to determine the transfer function for, here I will say the system And here I'll do quotes around the system under consideration because it is a little bit more complicated than just that. Because what do I mean? It is not just the system itself, but it's the input to the system and the system's output. But the reason we'll say system in this particular case is because the transfer function, as I'll get in your notes in a moment, was always assumed to be between one input and one output. So even though we could have multiple input, multiple output systems, even in classical controls, and we could work to try to analyze what was going on, we could only write a transfer function between one input and one output, and in most case, or in a lot of cases, analyzed in a classical controls class. Not that it really reflected reality, but in a lot of cases in a classical controls class, of course, the reason we can call it a system is because you really did only have one input and one output, in which case then the system itself was all captured by the input, the output, and the dynamic behavior of the system itself. But now you're going to see that we can start actually talking about other things associated with system descriptions, where really this idea of the system and its dynamic behavior and input and output start to get a little bit more, there's more nuance there, because we're really starting now to talk about potentially multiple inputs, multiple outputs, all associated with the same underlying physical system that's giving us the dynamic behavior. So that's something to kind of make a note of. So in classical controls, this idea of system included essentially the dynamic system, the physical system itself, in addition to the one input and the one output. So we just kind of lumped that all together as system, though we're going to start to see that that idea of a system breaks down a little bit when we start talking, potentially breaks down a little bit when we start talking about state space methods. So here, the transfer function, as I've been discussing, is defined to be transfer function in the frequency domain is equal to the one output that we're considering over, and that output represented in the frequency domain, over the input as expressed in the frequency domain. And the key was that the output is the input. We'll discuss that in a second. So here's the output. And X is equal to the input, or here, let's say U. And here, this is both for the system. So the one output for the system, generally assuming one output for the system, and generally assuming one input for the system. Now, the key is that the input has to be a placeholder input. It can't be a specific input when we're talking about the transfer function. Now, if you want to know the dynamic behavior of the system, then we will need to know the input, and then we can go ahead and use that input in order to solve for the output function y of t once we know the input. But the whole point of the transfer function is we're saying, no, we want to discuss what's going on independent of what's happening with the input. So we'll take a look at the ratio of the output to the input, all, again, all in the frequency domain. And then that's going to be considered the transfer function. And the key is the transfer function is a property of the physical system itself. Or maybe I shouldn't say physical system, the property of the system itself. And it is independent of input. So that's why we represent the transfer function the way we do and why we say it has to be a generic input, because we want to come up with, and the transfer function gives us that description of what's going on with the system without any consideration of what's actually happening with the input. We don't want to have a different description if we have a sinusoidal input versus if we have a step input versus if we have this or that. We want something that is a complete and constant, well, I don't want to say constant, a complete and unchanging description of what's going on with the system, because the system itself isn't changing. Its inputs and outputs are changing. That's all. Okay, so that's what the transfer function gives us. The transfer function is a property of the system. Now, the thing is that for these transfer functions, we assume that we're dealing with LTI, linear time invariant systems, which means that we don't have fundamental properties of the system that are changing in time, such as the masses that make up the system, those are remaining constant. Whatever stiffnesses or springy type members we have, those are remaining constant. Whatever damping or dampers we have, those are remaining constant. So that's what is going on with a transfer function, is we assume that we were dealing with LTI systems. Let's go down here. I think that gives me enough room. And so, of course, the transfer function itself, by definition, as we can see, because y is the output, use the input, right? There's only, in this case, we don't have a y1, y2, y3. We don't have a u1, u2, u3, just one y and one u. So by definition, can only be written between one input or a single. Let's do it that way. I like that better. And you'll see why in a second. A single input and a single output. And so here we say that transfer functions are only written for SISO, single input, single output systems, which we've already, at least I've already mentioned before. Now there is another limitation. That this idea of the transfer function cannot be used with non-zero initial conditions. So when we are working with transfer functions, it is assumed that the system has zero initial conditions for all the states that are associated with the system. And so, as you might remember, there are a couple different ways to get a dynamic system to do stuff. One is to have it have non-zero initial conditions. And an example of that is if I have a pendulum, the idea of a pendulum having zero initial conditions would be that the pendulum is just hanging perfectly vertically. And of course, if it is, it's not going to move. And so if I have a non-zero initial condition, that's me pulling that pendulum off to some theta naught value for its initial angle. And of course, then when I release that pendulum from that non-vertical position, what's going to happen? The pendulum is going to start to oscillate. And so that was one way to get a dynamic system to do something, was to give it non-zero initial conditions. Another way, of course, was to excite it with some kind of forcing function, some kind of input. And so that's what transfer functions assume, is that the only excitation for the system is coming from a forcing function or an input, and that nothing is happening because of initial conditions. There are zero, all the initial conditions are zero. So that's another limitation for these transfer functions, and clearly a pretty important one. And this only applies to linear. Time invariant systems, otherwise known as LTI systems. So then we can see, and as I was discussing before, the transfer function is a property of the system. If we are actually interested in what's happening with a specific transient response. So in order for us to understand what's going on with that transient response, obviously we have to know how the system got excited. And so, or was excited. And so that's where we need the input. So once the input is known, its impact on the output can be determined using, of course, the transfer function. So that gives you a little bit of a reminder, and because some of those specifics are easily forgotten, such as LTI systems, non-zero initial conditions, CISO, that's pretty typically emphasized in a classical controls class, but sometimes it's easy to forget that too, so that when you see a multi-input, multi-output system, back in your classical controls, or when you are working with classical controls, let's say that because maybe you haven't quite yet had classical controls yet. What you would do is you would just choose one input to look at, you would choose one output to look at, and you would write a transfer function between those two, and you would ignore the others. You would just say, nope, the other inputs are effectively non-existent. And then you'd write it between that one input and that one output. Then you could write it between that same input and maybe a different output, assuming that the first output you were looking at doesn't exist. And then, of course, being an LTI system, what could you do? You could just combine, once you knew what was going on at one output as a result of both of the inputs, because you could, of course, keep writing these transfer functions between any input and any output, then you would just sum together the effects, because that's the nature of a linear system, is that you figure out what's going on with input one to output one, from input two to output one, and the overall affected output one would just be a linear, the sum, I don't want to say linear combination, that's a little too general, would be the sum of what's going on with both of the inputs at that one particular output. So that's how you would handle that particular, or how you can handle that particular case. Now, fortunately for us, when we start talking about state space methods, we don't have some of those same awkward limitations. Because as you can see, there's some pretty serious limitations associated with the transfer function that is central to what's going on with classical controls. So the state space method, first of all, how does it differ in the way it represents things? It captures the differential equations. Okay, so now you'll see that things getting a little bit interesting. It captures the differential equations one as a set of first order. Differential equations. Here, I'll go back to diffeqs. And of course, what does that mean? That means that there are no derivatives. Higher than first order. And there's another limitation that we'll quickly discover in a moment. So we go ahead and we capture the differential equation as a set of first order differential equations, and then two, we will capture them in a specific matrix form. And that form is, we have x dot is equal to u times x plus b times u. And we have y is equal to c times x plus d times u. Okay. Now, I'll go ahead and start describing some of this, but let's just go ahead and describing what's going on here, but let's just go ahead and first name it. So this is called the state differential ran out of room there a little bit. If you'll give me a little license, I'll go ahead and just kind of scroll over and complete that and then scroll back. The state differential equation and the output. Equation, the first one being the state differential equation and the second one being the output equation. Okay, so before I go ahead and start defining all of these, let's go ahead and talk a bit about it, and then we'll go ahead and start writing again. So when we look at the form of these equations, clearly they are involving both matrices, and you can see how the notation we were already discussing when we were talking about the linear algebra review is coming into play here. So our matrices are A, B, C, and D. But then we'll also see that we have these things that are multiplying or being multiplied by these matrices X and U, but those are underlined. What does that mean? Those are vectors. And so what do we have? We have matrix multiplication of vectors that then lead to other vectors. One vector that is a result of working through the equation is the x dot vector, which is the time rate of change of the x vector that we see on the other side of the state differential equation. So the state differential equation relates the derivative of that x vector to itself. And so clearly that is a differential equation. We have the function itself related to its derivative. And so clearly that is a differential equation. And then we have the output equation, where of course we have the y vector related both to the x vector and the u vector through the C and D matrices. So we can see that this is clearly, these are clearly matrix equations. Just one of them is a matrix differential equation. So that is a very interesting equation indeed. So hopefully you're already starting to appreciate that. Now you're starting to see the intersection. And, you know, as I discussed before, the intersection of two very important, what are generally considered branches of mathematics, linear algebra and differential equations, intersecting here in these or for these state space methods would be the best way to say it. You might be looking at this though and saying, yeah, Professor Densmore, this is a great representation with the exception of one enormously glaring problem, which is not all of our differential equations that are coming from our fundamental laws are going to be first order differential equations. All you have to do is look to Newton's second law, and what do you get? You get F is equal to the second derivative of the position with respect to time. And right there you have a second order derivative, and yet this is a first order. This matrix equation is only capturing first order derivatives. And so what we're only going to be looking at systems that involve first order derivatives, and thankfully the answer is no. There is a very simple way around that particular what on the surface appears to be a particular issue, and you will start to see that very, very quickly when we start looking at the examples that will be a part of the next video associated with this first lecture on dynamic system modeling. So with that, we now see what's going on with these matrix equations, one being a matrix differential equation. And I have promised you that this idea of being first order isn't going to be as limiting as it might first appear. So let's go ahead and do our where. Because right now I've just been talking about X's and A's, B's, and C's, and I've been working really hard not to say things because I didn't want to spoil it for you. So here I'm just going to do my kind of colon here for these different things. So where A relates the state vector. So here I had to use the definition before I defined it. Actually, I think I just defined it implicitly now that I'm looking at things. So the state vector, that's our X. So our X captures the values of the states that are a part of the system that we're working with. So that could be position, it could be velocity, it could be some voltages, it could be whatever states we're dealing with, or a combination thereof if we're dealing with an electromechanical system. And so whatever states we can think of, thermal states, mechanics states, fluid mechanics states, again, voltages and electrical states. All of those things can be captured in the state vector. So the matrix A relates the state vector to its own first derivative. Now, it doesn't do it exclusively. It might in some cases, but it doesn't necessarily do it exclusively to its own first derivative. X dot, where of course X dot is representing how those states are changing in time, right? Because the whole point of what we're trying to discuss here with the transient response of the system is how things are changing in time. So the A matrix relates the X vector to its own derivative, i.e. how that vector is changing in time, or how the values associated with that vector are changing in time. And this is called the system matrix. So let me get called in here before. And as the name implies, this matrix is determined by the configuration of the system itself, and it is not dependent on the input. So this is a property, this A matrix is a property of the system. B, of course, relates what is called the input vector U to the derivative of the state vector X dot. This is called the input matrix. C, of course, relates the state vector to the what is called output vector. And that output vector is y. So you'll notice with the transfer function, we had an input u and an output y. We're holding on to some vestiges of that notation here, where little u is the input vector, little y is the output vector. But you'll also notice something kind of interesting with this notation that I'll capture here in just a second. But let me, if you don't mind, let me finish describing the different terms that exist, or the different quantities that exist in this particular set of equations. This, of course, is called the output matrix. And then D, which relates U directly. And the key here is directly. I won't underline it though. To Y. This is called the direct feed through. Let's put feed through on the next line, because I'll turn it into one word. Let's do it hyphenated. Matrix. And what that represents is if somehow an input appears directly as a component in the output and isn't modified by the system, then that's when it will be impacted, or that's when we'll see it in the D matrix. So, just a good way of looking at it is that the input just bypasses the system entirely and just comes in and does something at the output. And since it bypasses the system entirely, that's how there's no better way to capture it than through this idea of a direct feed through matrix. As you can imagine, there are a lot of systems where that direct feed through matrix really isn't having a huge impact on what's going on. But nonetheless, there are some cases where that could happen. And so that particular matrix helps us capture what's going on with that. So with that said, and here's where things start getting interesting, and of course I'll mention it and we'll write it down here in just a moment, is that first of all, you'll notice that I'm using lowercase letters specifically for the vectors. And that's because, and if you remember back to the Laplace transform, what was going on with the transformed function, the transformed time domain function? It was represented in capital form. So since, and the time domain function was in lowercase form. So what does that mean? That means that these state space methods, at least when we're putting it together in its traditional form, is written in the time domain. So we never leave, let's say it this way. Transfer functions forced us to go into the frequency domain. State space methods never force us or never completely force us into the frequency domain. We can choose to go there, and we get a lot of insight when we do. But as you can see, there's nothing here forcing this representation, and that's all it is just a different way of representing things. There's nothing here in this representation that forces us out of the time domain. And so that's why we're using these lowercase x's, u's, and y's, because it can all be written in the time domain. Additionally, and here is a really important distinction, is that we're dealing with specifically input vectors and output vectors. What does that mean? Well, vectors are a collection of quantities. So this state space method is not restricted to just a single input, a single output, unlike the transfer function. This representation can naturally handle multiple inputs and multiple outputs, which of course allows us to easily capture MIMO systems, multi-input, multi-output systems. And I'll get that in your notes in just a moment. So when we look at the state space representation, we actually have a lot of flexibility. It turns out that the set of states is not necessarily fixed, and I'll show that in the second part of, or the second video that will be a part of this lecture, where we can actually choose states that are different from one situation or one scenario to another, or let's say it this way, from one solution to another solution. It's perfectly fine. You end up in exactly the same spot if you want to, though what's going on with the intermediate representation or the representations on within the state space approach, that will change. But you should be getting, and you will get, the same output for the same input, regardless of how you select the states though, of course, the matrices will change accordingly to make sure that that consistency, that things remain consistent. So those things will change, but of course, since we have the same inputs and same outputs for our system, those will remain the same regardless of what kinds of states we choose. So here I want to make a couple notes. So even though we have some flexibility in defining the states, let's actually start with set of states. So the set of states should contain enough parameters to fully describe the system configuration. And no more. So you need to make sure, you need to be careful with your state vector that you are capturing just the right amount of states for that system. You don't have too few states, you don't have too many states. Another note is that the state vector, so since we have some flexibility, the state vector X is a set of parameters got my R in there a little too early. Is a set of parameters, of course, that is used to capture those quantities that are important. When attempting to understand the behavior, let me make that T a little cleaner, the behavior of the system. And again, I'll note does not need, so the state vector does not need to be the same yay, got system on in my brain, does not need to be the same in all cases. And that is extraordinarily powerful. Because what does that mean? that means, well, first of all, let's talk about that bullet a little bit. So when we're looking at defining the state vector, we need to be intentional and we need to be careful so that we capture the states as we are interested in them. We don't want to end up having states in there that really are things we're not interested in, because then to find what we're interested in, it's going to be more effort, a convoluted process, and the representation is probably going to be more cumbersome than if we spend some time up front and define the states how in a way that is most relevant to us. So, that's kind of good and kind of terrifying all at the same time. It's good because then we can focus on what we want to focus on. It's terrifying because there are decisions involved, there's choice involved, and we have to figure out what we want to do, what we're actually interested in. But also, what does that mean? And that's where this little sub bullet comes in, that the state vector does not need to be the same in all cases. Sometimes we may be interested in looking at a problem from one perspective, and that perspective may not lend itself well to a later analysis where we're kind of interested in something a bit different. And for the very same system, we could go ahead and redefine the states to make sure they align better to with what we are interested in, so that we can then work with a more efficient description of what's going on. But what we'll also see as we go through the class is that we can start working with things that you're already familiar with, namely called transformations, to actually transform the system matrix into forms where we can even more readily. And of course, when we transform the system matrix, we're transforming the states as well, so that we can more readily identify important information about the system just by virtue of working through that transformation. But again, you can't transform the system matrix without transforming the state matrix. And so we'll start to see that this idea of these states not necessarily being set in stone is an incredibly powerful property associated with this representation and this approach. So hopefully you're starting to see that things are much more interesting when we start looking at the state space approaches, and maybe a little bit more terrifying because you have to make more decisions. You have to think up front, and so a little bit terrifying, but also a lot more interesting than what is happening with classical controls. Okay, so let's go ahead and capture some of that discussion, some of that additional discussion, because I know I said a lot. So these equations, of course, include a first order as I already indicated, matrix differential equation. And here I'll spell it out just to make sure we don't excessively confuse. But here I'll go ahead and shorten the equation since I'm running out of room. And of course, as I also indicated, which has the perfect form for encoding the first order differential equations. You'll do diff EQs, developed previously back in step 1, associated with this approach. There we go. As I indicated, the state differential equation, and here I'll shorten equation, remains in the time domain and then of course my ominous add-on for now and you will see how things change and the additional insight we get when we actually take this differential equation, the state differential equation, and map it to something in the frequency domain, which we will be doing. So then we're going to be transforming this matrix differential equation into the frequency domain. So something to look forward to, but it will be a while before we get there. Clearly, since U and Y are vectors, specifically the input and output. But here the important thing, of course, as I emphasized before, are vectors rather than just individual scalar quantities. And here I'll even add in my respectively. Clearly this, this representation can, of course, can capture multiple inputs and outputs. And as I've mentioned a couple times before, this, of course, is a perfect way to represent MIMO systems, systems that have multiple inputs and multiple outputs. Now, one other interesting advantage associated with these state space approaches is that this approach captures the internal states. Now, when we look back at classical controls, what did we see? We saw that only 2 states were explicitly represented, the input state and the output state. But here with the state vector, we can see that internal states can be represented as well. So let's get states. Since it captures internal states, rather than just the input and output states, and here I'll just note that it was just those input and output states that were associated with the transfer function. then clearly this representation can provide significant insight into the internal got a little close there, sorry about that. The internal workings of the system. So we can start to understand, are the internal states observable? Controllable? Stable? Etc. So when we look at the transfer function, since we're not really looking at internal states, it is quite possible that we might have an internal state that is, in theory, going unstable, yet because of how the rest of the system is interacting with that particular state, it may look like we have a stable a transfer function associated with a stable system between the input and the output, though we have some crazy things going on inside of there. And the state space models give us that insight. So we can see if an internal state is, in theory, going unstable. Now, why do I say in theory? And this is very important, is because in real systems, there is no way for a system to really respond in a completely unstable fashion. What will happen is, and that's because we don't have infinite actuation. And so what will happen is that internal state will be mathematically unstable, and it will ramp up to some kind of generally very high output for that state, or very high values associated with that state. And then it will just kind of saturate because of the limitations of something that exists in the real system. So in theory, it's unstable. In practice, it's just going to limit out at very high swings in the value, more than likely, the state value. And so what's going to happen is we're going to see some really odd behaviors, because then the rest of the system is going to try to work with that. And it's possible that the rest of the system would try to compensate for it, but because it didn't really go unstable, then the rest of the system is doing some strange stuff, and we get some really, really bizarre behaviors that we wouldn't be able to explain using the transfer function approach. Whereas if we're using the state space approach, we would be able to look at it and say, oh, okay, this internal state is going unstable. And that's probably not a good idea. More than likely, well, let's say it this way. Not probably, it is not a good idea. So if you capture that there's some internal states that are going unstable, that would be something that you would want to correct, so that you don't see any strange behaviors that are associated with interactions that would have disappeared when, or appeared to have disappeared when we're looking at the transfer function, or at a transfer function. So this gives us a lot more insight. And this idea of a system that has an unstable state that never goes to, because remember, to be truly unstable, the state would have to continually swing to higher and higher, or continually take on higher and higher values. And so that's true theoretical instability. Because this behavior of essentially saturated instability has been observed so much, it's actually given a name called limit cycling, where the particular system will swing between very high values or very extreme values associated with the state, but it won't be able to go beyond those, provided it even gets to those values, because something could break before that happens, in which case then we wouldn't actually see it. We would just see those very high values. We'd just see a broken system. So with that, the state space approach gives us that additional insight we need to understand what's going on with those internal states, so that we don't run into problems because of something going on with the internal states that we would have that wouldn't have directly appeared in the transfer function, and we wouldn't have seen what was going on. So that makes this approach very, very powerful as well. Bringing in now more formally this idea that the definition of states is not unique. Which increases the value of this approach, because it allows us, it gives us that flexibility to represent the model in the best possible way for whatever we're trying to do. That is incredibly, incredibly important. So we can define different states or different state vectors, let's just say it that way. To, of course, make the analysis easier. So if we represent it in ways that we're interested in, the overall form of the representation should be simpler. And of course, it allows us to look at the system from different perspectives. And of course, that means that we can gain additional insights into what's going on with that system. Now, of course, states can be physically realizable, but as I said before, they can also be abstract. And this last one is generally used to make the math easier. But it can be used also to give us that insight into just what we're interested in. So hopefully this discussion has given you a better understanding. Well, first of all, has introduced you to state space methods and has given you a better understanding as to what some of the properties are associated with that representation, why those properties are as exceedingly important as they are. Again, a lot of different advantages. We get more insight, It's a more flexible way of representing what's going on with the system, etc. One other thing, and this will be my final parting comment for this part of the lecture, and I'll just go ahead and, as I indicated before, I'll use this OneNote page for the examples. So we'll be picking back up here for the second video. One additional advantage, of course, is that the matrix format makes it easier, of course, for computers. Because, of course, computers love arrays of numbers for computers to efficiently analyze the system properties. And responses. So hopefully you can see how these state space, or how this idea of the state space approach really adds a new dimension to how we can look at what's going on with dynamic systems, and of course, eventually how to control those dynamic systems. But remember that this is a general way of representing a dynamic system, a system that has a transient phase to its response. Because what are inputs? Inputs are just how the system is being excited. What are the outputs? The outputs are just what you're observing for that system. So it doesn't matter whether you're looking at temperatures for a thermal system, or whether you're looking at fluid velocities for a fluid mechanics system, or whether you're looking at positions and velocities for a standard mechanics system, or whether you're looking at voltages for an electrical system. It's irrelevant. It's just, what are you looking at? And those become your outputs. And how are those outputs being influenced? And that's where we're coming in together with, or we're coming in with this idea of inputs. And of course, one of the things that you'll notice I didn't indicate as a limitation for these state space methods, because it's not, is that state space methods can actually handle non-zero initial conditions. And so that's another nice thing that's associated with them. So with that, I will go ahead and call this first part, or this the video associated with the first part of this lecture, a wrap.